Section 13.2, this is the calculus of vector-valued functions. Here we introduce some ideas of how we can take limits, derivatives, and integrals component-wise of, excuse me, of vector-valued functions. So limits, I mentioned in the first video, the introduction to this overview, that limits will not be covered on the final exam, so we will not be doing limits. And really, differentiation is pretty much the one thing that we continue doing all semester. I mean, right now we're doing integration, but we are integrating, we're not usually integrating vectors at this point. We may be integrating a vector field, but the way that we integrate a vector field is we use a parameterization, and then we ultimately take a dot product. So by the time we're integrating it, it's no longer a vector. So differentiation really is something that we continue to do all semester. So, but this idea really is if you have a vector that has multiple components, if you want to take the derivative of this, then you can just take the derivative of each component, so on and so forth. What is most important here in this section is the tangent line. So 13.1 shows us that this right here is a path parameterization. So this would trace some sort of path in 3 dimensions. So here are our 3 space axes, and let's say we have a path here that's being traced like this. Something like that. I'll put some orientation lines on here so we can see how this is being traced. Okay? So let's say this is the path C, and C is traced by R of t. Okay? So now let's suppose that there's some location on this curve. Let's say let's do right about here. Okay? So let's say this is, well, let's make it match this, where let's say this corresponds to some t value of t naught. So at this point, there is a tangent vector. So if this is the location that corresponds to t equals t naught, then this vector right here is the tangent vector. Or it's a tangent vector. Oops. Let's say, really, I guess we could call this the velocity vector. Which is a tangent vector. To the path C at the point corresponding to t naught. So now, effectively, this vector, this is the direction vector. Of the tangent line. We already talked about lines, parameterizations of lines in general. In general, a line is parameterized by a direction vector, which is just a vector that points from the origin to some point on the curve. So in this case, that would be this vector right here. A little small, but it's this one right here that I just drew. That's a vector that points from the origin to this point. And what is that vector here? Well, that vector is just r of t naught. It brings us to the point on the line, plus t times our direction vector, which we just said this is our direction vector. So t times the derivative at t naught. So this is the direction vector. Oh, excuse me. I meant to say this is the position vector. Pardon me. This is the position vector. This is the direction vector. The position vector brings us to the line. The direction vector tells us what direction to move in thereafter. So that's exactly what we have here. Little reminder here that when you are asked to parameterize something, make sure you provide a domain. Sometimes we ask you guys for the parameterization of a line. Sometimes we ask you for the parameterization of a line segment. So if it's a line, then our domain is going to be all real numbers. Like t will range over all real numbers. But if it's a line segment, depending on how you parameterize it, if you parameterize it the way that you were taught, and not some other non-standard way, then t is in the closed interval 0 to 1.